Hello everyone, I am Arajo, the PhD candidate in Wageningen University in the Netherlands. I'm going to talk about the vegetation uptake of the carbonyl sulfide, and I will show you how to improve the estimation scale of it in the biosphere model SiB4. Why we should look COS? The COS is a chemical compound in the atmosphere, and it's generated mostly by ocean and consumed by plants with photosynthesis. To be specific for photosynthesis, COS has similar pathway into leaves with carbon dioxide, but it does not respire, so that it can be a proxy for gross primary production (GPP). However, so many questions are in a COS uptake, especially in the enzyme activities. The study aims to better understand the COS leaf uptake, and then we apply it into CF4 models to improve simulation abilities. Before knocking the door, we should diagnose the current address of CF4. So these plots about how CF4 estimates COS leaf uptake well corresponding to the temperatures and stations. So overall, the blue dot, which is estimated COS flux, are increasing to the temperature, whereas the black dot, which is observed one, has a curve with the optimum temperature. We focus on finding what is the right patterns of enzymes temperature response from the observations. The SiB4 is the biosphere model and known as well made for the carbon cycle in the biosphere. And COS can be simulated by multiplying the COS mole fractions in the air with a series of the conductance in the model. As for the mole fractions, we use the optimized values from TM540 assimilation system. And regarding conductance, we assume that stomata and boundary conductivities are accurate because they are used in the GPP estimation, which has a quite good accurate. So we focus on the enzyme activities, which plays the large roles in the simulation of COS uptake. Here, the react enzyme is carbon anhydrase. We called it as the CA in this study. And what is the problem here? Since we don't know about the CA's properties well, SiB4 adapts the linear relationship with the enzyme Rubisco, which is CO2 enzyme, is patterns. So we explore CA's response to temperature with its kinetic. To know CA's activities in leaves, we need observations. So we use the fiber FluxNet data. Utila is for the evergreen needleaf case, and Harvard Forest and Sorrow are for the deciduous broadleaf case. As for C3 glass, we use the newsstrip and the last Matadas dataset. Since there is no observed CA activities directly, we changed this COS uptake equation to find internet conductivities like the lighter side equations. And regarding COS mole fractions and the COS assimilation, we used observed data, but also we used the modeled values for the stomata and air boundary conductance because they are not observed directly as well. Generally, enzyme responds to temperatures, and we adapt the equilibrium model to describe it. In this model, enzyme acts to the temperature with the equation as shown the lighter side. As you can see, there are some variables, and we can choose the key factors as these four variables. And then these four vectors can determine the patterns of the enzyme's activities. The first factors is the kcat, that is the enzyme catalytic rate constants. The second is the activation energies of the enzyme reactions. When you see the left figure, it is about enzyme kinetics. So in leaves, reactant can be changed as the product when it obtain the energy. So the red line is about transition without enzyme, and the blue line is the same but with enzyme. To transit the form of the reactant, the active energy is necessary. The third one is delta H equal is the enthalpy changes between inactive and active phase. And the fourth one is T equal is the midpoint of the temperature response. So regarding two variables, when you see the right figures, the enzyme acts to the temperature with a curve, and this curve gradient is affected by the T equal and delta H equal. So to determine four key variables, we use three kinds of hypotheses here. So first, those key factors are related to the CA's activity and it is not changed for a short time. So we will find the factors in stationary. The active energy delta HA is intrinsic properties, so we use it as a fixed value. The second, delta H equal is sensitive to temperature tolerance. We use the standard variation of yearly temperature as the inverse directions. So if standard variation is large, that means delta HQ is small. The third, T equal is related to habitat's climate temperature. So we use the mean of yearly temperature to find the value. If habitat is warm, then leaves T equal is also larger. With several hypotheses, we optimize the equilibrium model to find the best values for parameters. So we use the cost functions with deviation between hx and y. So the hx is the estimated enzyme conductivities from the equilibrium model, and the y is observed conductivities. And those four factors are optimized to minimize the cost functions. And there is the error term that is R, that is for the weighting the deviation, and we applied it as the standard variation of the enzyme, observed enzyme conductivities. And I also write the number of the data point sets, and especially the sorrow, it has the small points, so you have to keep in mind. Now I will show you the result of optimization. First, we looked for the best catalysis rate for each stations, and we found the values as right figure. And second, the target is the delta H equal, which is enthalpy changes between inactive and active phase. According to the hypothesis, delta H equal is lower at the high standard variation of temperature. And I think the result matches well to the hypothesis. For instance, the smallest delta H equal, which is the blue line in the Harvard forest, HVFM, that has the highest values of the standard variation of temperature, so that it is matches to the hypothesis. To find the best delta HA and T equal, which are the activation energy and the midpoint temperature, we examine what temperature has the peak values of the COS uptake. So the figures shows a diurnal cycle of observed COS flux as the black line and the air temperature as the red line. So the key point is that we are looking for where is the optimum values of the COS uptake. So these yellow circles can represent where it has, and these values had range of temperature. So the optimal temperature should be larger than this range of the temperature. Also, the T equal is related to habitat temperature, so we made the direction of T equal with the mean temperature in each station. So with these ranges and the first conditions, we found where is the best values to the delta HA and the T equal. So it is shown as the yellow circles. And we conclude that delta HA is about 60 kJ per mole. At the same time, we found the best T equal for each stations, like these figures. So to sum up, we found that the optimized four factors, they have linked to hypothesis very well, and especially as for the catalysis rate, Kcat, it can be classified to the plant functional types, and it has the differences in a warm and cool habitat. So as for the evergreen needleleaf forest, it has the smaller values than deciduous broadleaf forest in the KCAP values. This slide is about how our equation can describe the GCA curves to the temperature. With optimized factors, when we estimate enzyme conductivities, which is shown as the red color, it matched well to the black dot, which is the observed GCA. And our optimized GCA has, I think it is powerful because it explains the observations patterns overall, and also can capture the denaturing point compared to the original SiB4 GCA, which has the sky blue dots, and the others CA estimation, for instance, the soil model of the COS that has the yellow dots here. When we compared optimized COS flux with observed flux, the root mean square errors and mean biased error are improved well. Especially current SiB4 tends to underestimate uptake for large COS uptake ranges, but our optimized SiB4 can capture these ranges very well. As you can see, it is almost the diagonal line. The improved performance is also found in the diurnal cycle for all stations. Generally, a prior flux, which is the blue line, shows under values compared to the observation, which has the black dot line. And regarding this problem, our optimized SiB4 remedied it well, and when that is shown as the red line. But still, there is the many places where we have to consider as the limitation in the heat yellow and the last Matatas cases. So we need a further research. Okay, so let's go back to the first figure. Here we add the optimized COS uptake as the red dots. As you can see, the red dots can make a better estimation in the similarity of the variation in heat law, and it can follow fluctuation in sorrow, especially the denaturing patterns, compared to the blue dot, which is the original SiB4 model. So I'd like to stress important point for this study. So to understand COS leaf uptake, we focus on the internal conductivities, that is the enzyme conductivities, which is related to the enzyme activities, and it has large roles on the COS uptake. The main problem is that SiB4 uses the Rubisco activity, which is not exact enzyme for the COS. So SiB4 cannot capture the denaturing COS flux at the high temperature. So we looked for the enzyme carbon anhydrous behavior, which is main component for COS uptake. We apply the equilibrium model and optimize the critical values for the each stations. As a result, optimized COS uptake shows almost a similar pattern to observed uptake, and we are looking forward to using it to learn global COS flux and finding a better not only COS but also CO2 purchase for the next step. So that is all. Thank you very much for listening.